Okay, then in terms of the classification algorithms, we can also classify it in different ways to characterize what kind of problems they are designed for. The first thing, we have the order of the algorithm. The order can be 0, first, or second. A zero-order algorithm basically means that it doesn't use any derivatives, so it's derivative-free or gradient-free. So this kind of methods we're going to look into in part 4 of this course. And then we have the first order algorithms that use the gradient, because gradient is the first order derivative. And then second order basically means that you also use the curvature, which is the second order derivative of your function. And you can imagine the more information we use about our function, the more efficient the algorithm would be in general if you compare it side by side, apple by apple. The other way to classify is by the search direction. It could be a local search or it could be a global search. A local search does something like this. So you start in an initial point and then you step locally to different points in your neighborhood, and progressively, iteratively, you would then converge to the optimal solution. So this search only searches the surrounding area of your function, and it doesn't always guarantee that you would converge to a global optimum, because if you have a multimodal problem, if your search starting point is near one of the local optimum but not the global one, you would converge to that local one instead of a global one. And this is indeed how a lot of gradient-based methods work. So gradient-based methods, which is what we're going to look at in part 3 of this course, we typically pair it with a global search strategy to increase our chance of actually getting the solution that is a global optimum. And some examples of a global search strategy could be a multi-start strategy, where you run a lot of different optimization runs, and each time you start in different initial points so that you actually find the best optimum out of all of the local optima you have identified. Next, we have the principle. So what principle is the optimization algorithm based on? It could be mathematical based or it could be heuristics based. So gradient-based methods are one of the mathematical based methods, and a lot of the gradient-free methods coincidentally are heuristics based, for example, like the genetic algorithm. And the difference between mathematical based and heuristics based is that for mathematical algorithms, you often have a very robust and mathematical theory justifying why this algorithm works. And there would be very clear and rigorous proof for that algorithm or rigorous condition that you must satisfy in order to find the actual true optimum. For heuristics, it's more like using common sense to devise an algorithm. It's more like using common logical reasoning to devise the algorithm instead of using very mathematical, rigorous way of proving that this algorithm would work. And heuristic algorithms also have a characteristic where they won't really give you the true optimum. It won't give you the absolute best solution. But what it does is that it will give you a good enough solution that you can judge for yourself whether you want to accept it as your final solution or not. So it's sometimes more pragmatic in that sense. And for a lot of engineering problems, heuristics-based methods could be a valid choice because it's good enough and it's faster than other gradient-based methods. Sometimes you just don't need that extra margin of the best and best performance. As long as the solution is past a certain limit and is good enough, then you're happy to take it as the final answer. And then we also have the function evaluation, which could be direct or which could be using a surrogate model. A direct function evaluation is simply when you have the function such as the objective or constraint function, and you plug in the values into that equations and see what the output is, what the result is. But a lot of the times the function could be very expensive to run or very computationally intensive. For example, like a CFD model. So CFD model, there are tens or thousands of equations in it that needs you to solve it before you can have a solution. So for a particular design, you could either put it into a CFD model and wait for hours or days to come up with the output, like the lift or drag of a particular wing design. But you can also use that CFD data to train a surrogate model, which could be a neural network or a response service that allows you to use a lower fidelity model to mimic the behavior of that CFD model. Although with a loss in fidelity, you can actually regain the time it takes to run this model. And it could be useful in certain scenarios, especially in the initial exploratory phases where you don't need an exact solution, but you want some approximate solutions and you're happy with it. Then using a surrogate model to evaluate your function could be another valid choice. And then we also have stochasticity, which we talked about earlier. An algorithm could be designed for deterministic optimization, or it could be designed for stochastic optimization, which are topics surrounding reliable and robust optimization, where you don't just optimize for a deterministic objective function, but you actually include or consider the uncertainties involved in the function. Then in here, we also include time dependence for completion. Time dependence could be static or dynamic, so you could be optimizing a dynamic problem like the control laws of a robotic arm. So it is a very dynamic problem because based on different inputs, you need to very quickly output an optimal control strategy, an optimal control output. And those are dynamic problems in optimization. But because this course is developed for engineering design, we don't really consider time dependence in this regard. But nonetheless, this is also a kind of optimization algorithms, and there's also a big area of optimization problems as well.